class. Wow. Checking the string. All right. Let me get so this is Benoullis equation, and so here's the thing: E plus gamma z plus rho z squared over 2 is equal to a constant. This is very much like mgh over a volume, 1/2 mv squared over a volume, and f dot x, or d, over a volume. This is kind of the applied force, so to speak. But it has to be constant along a streamline. So theoretically, let's start with a point back here, say 0.1. Now, if you zoom in really close, you might have 2 neighboring or 3 neighboring particles. They may all be, or they will all be at the same elevation, the same constant, whatever this is, whatever that number is going to be constant across all of them. So I'll have one particle. It'll end up going out here. I'll have a neighboring particle which may end up coming up here, and another neighboring particle which comes out here. So I'll call this 3. because 4. Legally, I can only write, here I'll set this one, I can write between 1 and 2. In other words, P1 plus gamma Z1 plus rho Z1 squared over 2 is equal to P2 plus gamma Z2 plus rho Z2 squared over 2. So I can write between location 1 and location 2. Legally, I can't write between 2 and 3. But I can recognize that all of the constants originating here are all the same, and they all end up at either 2 or 3 or 4. So legally, I can't do the 2 to 3, but since they all originate at 1, I can write 1 to 3 and 1 to 4. But this is the same 1, so in fact, I can write from 2 to 1 and then from 1 back to 3. So in fact, I can write between these because there's an intermediate where they're all of 1 is at the same energy. Now, if you really wanted to be a very big stickler, you would say this is 1, would be 1 prime, this would be 1 double prime. Essentially 3 different locations that end up either at 2 or 3 or 4. The energy between these, all these particles, is the same constant. So theoretically, I can write between 2 and 3 and 4. So this means I can do this. Equals to P3 plus gamma Z3 plus rho Z3 squared over 2, which also equals to P4 plus gamma Z4 plus rho Z4 over 2. So the energy is the same at this spot, this one, and that one. Now, let's identify a couple things. I know that. I know when you open the faucets, you can basically say the P gauge pressure is equal to 0. Now, I can't say that about 1, but I can say that about 2, 3, and 4. But I can go back over here, say, ooh, that is weird. Let me try that again. Uh-oh, something is very bizarre here. Hang on. Okay, don't know what happened there. I can't say that about 1, but I can say that about 2, 3, and 4, because the faucets are all open. What else can I say? Well, first, I need to pick a datum. I'll go ahead and make this the datum, and I'll call that Z. If that's the case, it tells me Z4 is equal to 0. It tells me Z3, which is this location, is 4 and 8, or 12 above it. And Z2, which is the very top, is 2. So if each of these is 12, and I move up 4, all of them are 12. Each of the faucets is 12 foot above the other. That's 24. Now, I can go in and put this in here. 24, 12, 0. Okay, I don't know the velocity of 4, and I don't know the velocity of 2, but I do know the velocity of 3. It's 20. one is 20. Suddenly, I have one of the values that I can figure out the constant from. That's the constant here. So I'm going to go after that. I'm going to basically say gamma 12 rho 20 squared over 2 is equal to the constant. This is water. So since it is water, that's going to be 62.4, and this is going to be 1.94. If this is in feet, yes. So my constant, okay, wait a minute. No, we're not moving. Okay, well, here, I'll do it this way. I guess the keyboard is on. Hang on. Let's the keyboard is not on. That's the problem. Okay, now the keyboard is on. It wouldn't be very good to enter data if you can't enter it through the keyboard. So, here. 62.4, 12 plus 1.94 times 20 squared over 2, 1136.8 is equal to the constant. That's your constant. That's the constant that sits here. Now, he didn't ask us anything about 1, so I really don't care about that. But now, he wants to know the velocity at 4 and the velocity at 2. So, I'll start by taking this one, and then I'll put this one next to it. So here's what I mean. Okay, so if I take this equation, I'll say rho v4 squared over 2, I won't have a value here and I won't have a value here, is equal to, you take this one, gamma times 24 plus rho times v2 squared over 2 is equal to the constant, 1136.8. Let's start with the simplest. If I want to know V4, velocity out of the lower faucet, then 1136.8 times 2. Now I'm kind of ignoring this for the moment. I'm basically working between these two. Okay, so I've got 2 divided by rho, which is 1.94, and then I have to take the square root of it. So, yeah, there you go. Yep. Trees might get wet there. I tell you what, here's what they might do. They might be on fire and they might need to get wet. So here's a bunch of flames. So the trees are burning. And you want to be able to use this faucet to put them out. Okay, what's the problem with that? I'll show you the problem. First, let's solve V4. So there's that. Then you multiply that times, let's see, square root of 1136.8 times your 2 divided by your density, 1.94. That's in slugs per cubic foot. Okay, 34.234. That'll be in feet per second. Okay, so yeah, we got our answer there. Now, let's try to find velocity of 2. Because the velocity of 2 is what you're going to use to connect your fire hose out and put out your burning trees. Okay, I just changed the problem. Here's the forest fire outside your yard. It's getting really, really big. Okay, so here's what you do. Here's your problem. Okay, so now I take your gamma, 24 feet, then, all right, hang on. 24 feet plus 1.9, well, I'll go ahead and leave this density right now. Density, you want to find V2, okay, V2 being the velocity out of this faucet, comes out of this faucet. Now go into a fire hose, but I'm just saying, maybe you don't have a fire hose, maybe you just have like a tray that goes out here and puts out the fire. Okay, and your Benoullis constant, or the energy state, is this. Now, this is 62.4, 24, plus 1.94, density, slugs per cubic foot, V2 squared over 2. Now, take this to the other side, you get 1.94, V2 squared over 2, 1136.8 minus, this is a good one, 62.4 times 24 gives you 1497.6 equals to, this is a problem. Why? Because 0.8 minus that becomes a minus 360. Now you can do anything you want here, but here you go, minus 360 times 2 over 1.94, and guess what you get? You're in imaginary space. So suddenly, how do you do that? Velocity equal 1. What? It actually non-existent. It won't come out the faucet at the top. And if you look real close, take a look here. So the author gave you some indication that has a nice little blue stream coming out here. A nice little blue stream of water coming out here. Nothing coming out here. The water won't come out the top faucet. Actually, the fire will rage until you're standing inside and your head catches on fire, and you think to yourself, why did I not try to figure this out by doing the fluids class? Well, I don't know. Okay, so there you go. There's Benoullis' equation. Let's go to the next problem. Here you go. Water from a pressurized tank through a 6-inch, which is 6-inch diameter, pipe exits through a 2-inch diameter pipe at the top and rises 20 foot above the nozzle as shown. Determine the pressure of the tank if the flow is steady, frictionless, and incompressible. No losses. Means you can use Benoullis' equation in its most primal form here. A list here is 1, list here is 2. T1 plus gamma Z1 plus rho V1 squared. Again, this is the same thing as F dot X per unit volume and applied load. If you look at this, this is mgh over a volume. If you look at this, it's 1/2 mv squared over a volume. It's an energy equation per unit volume. Nothing more than that. I have no losses, frictionless, no losses. If I had losses, I'd have some sort of head loss here, which we'll get to that later. That's chapter 8. T2 plus gamma Z2 plus rho V2 squared over 2. All you got to do is fill out the information here. he tells you, or he asks you, what is the pressure at 1? Determine the pressure in the tank if the flow is hit. So this is what I'm interested in. So I'm just going to list it. P1 plus gamma Z1. Well, if I want to make my life simple, I'll take my datum here. There's my Z. So first thing I realize is that's 0. Plus, what's the velocity at location 1? Location 1 is the top of this water. Now, here's an assumption that you do a lot. Yes, the tank is draining. Yes, this diameter is a big diameter, little diameter. The mass flow will kind of give you an indication that the velocity here at 1 is very, 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 very small compared to the velocity up here, which gets squared and it's pretty fast. So it is totally legit to assume this to be very small and therefore almost non-existent, because if it's small, 0.00001, square it, you get a whole bunch more O's. 1. So what happens is on the left hand side you just get P1. What do you get at 2? Well, identify this. The water hits the very top here. It's in atmosphere, so my gauge pressure is equal to 0. It's at the very top, so the water is stopped. It's stagnating at the top. You know, it's hitting the top and falling back down. It tells you how high it is. Technically, okay, water exits the vessel is 6-inch diameter. Here's your 6-inch diameter. I really don't care about that. Exits through a 2-inch diameter nozzle and rises 20 foot above the nozzle as shown there. Now, we may actually have to add something here. Okay, wait, what's going on? Okay, my pen is geeked up here. There we go. Okay. P2 at the top, nothing. Gamma Z. Now here's the problem. I don't really know. Technically, he has left me with a gap here in that. And this happens in this book often. So where is the elevation of the water? What is the difference between here and here? Well, I don't know. So I'm just going to call this an H and leave it at that. And what you'll find out is he will work this problem, and I can bet you money we can look at the answer in the back of the book. We're going to make an assumption about that H. But here's what we're going to say. Elevation there is gamma, times H plus 20, plus, what is the velocity at the top? I can list a 0, or I can just write it down. I mean, I can basically do that. And technically, P1 should be equal to this water, right? Yeah, water, 62.4 pounds per cubic foot times 20 feet. Now, what about this H? You know, that's a little bit of an annoying side. Here, I'm going to calculate this, and with this one, I'm going to go look at the back of the book. 62.4 times 20. Okay, what is that? 1248 pounds per square foot. All right. So I normally wouldn't do this, but I'm going to go look at the back of the book because I'm going to look at this gap here and say, hey, what did he do about this? What did he do about this right here? Let's see. The book. I think, let's see if I have the, oh, it's the whole book. So, okay, so I'm going to have to remember the number. 338. Now, unfortunately, okay, I'm on page 169. I'm going to write that down because I'm going to need to come back to here. And I'm looking at column 338. I don't know, 760. A little too far. So here's your problem. 1248. Now, this is annoying. This is one of those things that really annoys me. It's 1248, right? So he calculates that. But in fact, that's not what the answer is. The drawing is not consistent with that. Because there is a gap right here. That gap should be added because if that's like 10 extra feet, then that should be in part of the calculation. So he has made an assumption that this h is equal to 0, when in fact he's clearly drawn it on the diagram as though it is not 0. So, yeah, it's just one of the things they do in these books sometimes. There's not much you can do about it. So when you find this, you know, it's just life. So, yeah, let's head off to the next one. Okay, the next one. Water, which is assumed inviscid, which means no losses. Why? Because the viscosity is what creates the losses. So if it's inviscid, it has no losses because the losses are occurring because of the viscosity. Flow is steady, that's a Y. And the vertical, oh, that's very steadily. Uh-oh, there's probably some other word there. In the vertical variable area pipe shown, determine the flow rate if the pressure in each gauge registers 50 kilopascals. Oh boy, when SI, oh boy. Okay, so what you do, oh, okay, something went off there. It's okay. So what you do here is you list location 1, you name it. This location 2, I'll just name it 1, I'll name this 2. P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. No losses, or you would have a different energy at the beginning as you would at the end, but you don't. So, datum, you pick your datum like that. P1, he registers both of these. So, I like to list it with all that. Newton meter squared plus gamma times Z1. We got gamma 10 meters times 10 plus rho V1 squared over 2 is equal to 50 plus, okay, now the datum here at 2 is 0. Gamma times 0 meters plus rho V2 squared over 2. So guess what happens here? That cancels that. That goes away. So what you end up with is 10 times, and I will tell you that's rho times G, which is for water, it's 1,000 kilograms, meter to the cube. G is still 9.81 meters per second. So you get 9,810 newtons per meter cubed, and you get a meter here. So this will be pascals that comes out of this. Then you get plus rho, which is still 1,000. V1 squared over 2 equal to 1,000 V2 squared over 2. Now, you don't know V1, you don't know V2, but what you do know is, you know, the diameter here is twice the diameter here. I'm assuming they're diameters because this kind of indicates sometimes that it's a sliced off section that's a height, pi r squared, you know, that kind of stuff. So what I will do is I'll say the area of 1 is pi. The diameter there is 2 squared over 4. The area of 2 is equal to pi 1 squared over 4. So now how do you use these? Well, your flow rate, your volumetric flow rate is the same no matter what. So A1 V1 is equal to A2 V2. You don't know what it is, but what you do know is you can put this in here and put that one in there, and what you'll get is pi, for the first one is this, 2 squared over 4, V1 is equal to pi 1 squared over 4, and V2, cancel that and that, and what you'll get, 4V1, 4 times V1 is equal to V2. So if you take this, whatever the velocity is here, multiply it times 4, and that's the velocity here. It's sped up because it shrank down in the area. It so happens it shrank down such that it becomes 4. Guess what you do? You take that, put it in there, and then you get 9,810 with another O right here, plus 1,000 V1 squared over 2 is equal to 1,000, how about that? 4 V1 squared over 2. Why? Because I took the V2 from here, stuck it in there. Now my equation says 9,810. That's because 9,810 times 10 is 98,100. I can divide 1,000 out of all this, but I won't right now. Okay, so I'll move this to the other side. 1,000 over 2. 4 squared gives you 16. V1 squared minus V1 squared. That's because that gives you that, and that gives you that. So now you'll take the 981 extra digits divided by 1,000 times 2 is equal to 15 instead of 16. V1 squared. Now you can take V1 is equal to take 9, 8, 1, 2 zeros over something with 3 zeros, a 2. Might as well take the 2 up, divide by 15, take the square root, and oops, wrong place. Okay. Square root of 98. Times 2 divided by 1,000, divided by 15, and then I got to close all that out to actually, caps lock was on. It doesn't like that. 3.61 3.61. I don't know. I'm writing down those extra digits. Now, before I go any further, determine the flow rate. Okay, he wants to know the flow rate, not the velocity. So what I need to do, that's in meters per second. So what I need to do is figure out the Q. A1V1, which is equal to 3.6166 times pi. Okay, A1, the diameter of 1 is the 2. So that's going to be 2 squared over 4, because this is pi d squared over 4. Uh-oh. I don't know what that was. Because it's pi r squared, if you put in d over 2 equals to r, then you get a 4 on the bottom. So what is that equal to? I don't know. Take the number you got before, multiply that times pi. Oh, and then that's it. 11.362. And you know what I might do? I might just check this and call it quits for the day, because we're moving fairly rapidly through it. What's the problem number? 347. I'll quit only if oh no. Okay, well, there is no 347. Doesn't matter. If you find a mistake, it's all good. I guess these problems are only even distributed in the back if I look at them. 12, 14, 16, 18, 20, 22, 24. Yeah, it looks like it's all. I should have known that. It's all good. Well, maybe I'll do, let's see what I have for the next problem. Yeah, let's do this one real quick and then we'll call it good. Okay, so this one's quite interesting. Water flows through pipe contraction shown here for the given 2 meter difference. And then when I determine the flow rate as a function of the diameter of small pipe. Okay, so here's the deal. You pick a spot back here, name it 1. It ends up at spot 2. Here's what you do. V1, then a V1. V1, let's row V1 squared over 2 is equal to P2. That's then as V2 plus the row V2 squared over 2. Now, legally, you shall do, you'll zoom in here, and you'll pick a tiny spot just south of it. Call it 1 prime. The elevation difference between these two is 0.0000000R1 e to the minus 100 meters. No difference in elevation. But what this particle does, it goes around it. This particle stagnates on it. And then this little green particle runs down through here and out the end of the pipe. So we'll call this location 3. Now, we can write between 1 and 3 because, not because Benoullis says we can, is that because these two are at the same energy level. 1 only goes to 2, 1 prime goes to 3. But the energy between these two is the same. It's a distinction that's often passed over in fluids that adds some confusion here. Okay, rho V3 squared over 2. Now, let's first identify the datum. Datum starts from here, meaning these are all 0. So again, P1 is V1 squared over 2 is equal to, and guess what? V2 is what? Stagnates, has no value. P2 equal to P3 plus rho V3 squared over 2. Now, you get this, and you get this. Alright, this is a really bizarre one here. It's odd too. Here's your deal. Okay. How do you write the diameter between these two? In other words, B1, A1, or pi 0.1 squared over 2 is equal to pi d squared d3. Now, this is something I know between the relationship between 1 and 3, not 2 and 3. But 2 is sitting there by itself. Believe it or not, if I want to list this as some functional value k, and P2 will be equal to k plus 0.2 times the height. Now, what's funny is P3 is just equal to k times the height. So let's write these down one more, okay? P1, that's rho V1 squared over 2 is equal to k plus 0.2, that 0.2 meters, h equals to k h plus rho V3 squared over 2. The k's cancel each other out, so on the left-hand side, you're left with 0.2 h equals to rho V3 squared over 2. But guess what? If you cancel those out, you can't leave it out of there. So if you have this, that does not equal that. What it equals to is k times h. Now, water flows have determined the flow rate as a function of the small diameter pipe. Guess what? There isn't an ability to do that. You do not have the ability to do that. You cannot do that here, because velocity 3 and velocity 1 are related through that. It's simply not possible. In other words, all you need to know to find the velocity of the pipe is one tube right there. You don't need the other one. Now, the reason I bring this one up is because in the next problem, this one makes better sense. So what I'll do is I'll list this one real quick, and we'll make sense of this one. Here's location 1, location 2. Do the same way, same thing. There's no third point here. Gamma V1 plus rho V1 squared over 2 is equal to P2 plus gamma V2 plus rho V2 squared over 2. Elevations, the same. Pressure at P1, there you go, some distance K, I'm going to call it K, so that's going to be 0.2 plus K times H, that'll be the pressure at 0.1, plus rho V1 squared over 2 is equal to, guess what the pressure is? 2 is. The column of water above it, or K, and gamma, with rho V2 squared over 2. Alright, now I can simply say 0.2 H plus rho v1 squared over 2 equals to rho v2 squared over 2. Now, I can use this relationship between these two. Mainly, pi 0.1 squared diameter over 4 comes v1 equal pi d squared over 4 v2. Now, what do I have? I can cancel this and this and this and this out, and I will get, what do I want to do? Say I want v1. I can choose one or the other. You know what? Yeah. I'll choose v1 equals to v2 d over 0.1 squared. Now, I take this and put it in here. 0.2 h. That is not an h, that is a gamma. I was going too fast there. And just pull down. Sorry about that. Okay, 0.2 times gamma. Rho v1 squared over 2 equal to the, okay, I'm reconnected. I think I'm going to drop the line and go on from here. I'll pick this up on Wednesday. Oh, wait a minute. Word of the day. Sorry about that. I just get in here and get going. Backpack. How about that? There you go. There's your word of the day, and we'll see you Wednesday.